In example 7, we're going to go ahead and solve the logistic growth differential equation, and you're going to see why in just a moment. This is a BC only topic because it's going to use some other BC only concepts in order to solve the thing. So let's go over here. We're going to need quite a bit of space. If you have yourself where you're taking your notes or whatever, make sure you reserve yourself a couple of pages for this, as you'll see. All right, so here's our differential equation. We're going to solve this thing for p, basically, just like we did with the regular exponential growth one. And you're going to see that that one was a baby model compared to this one for sure. So what's the first step involved in solving a differential equation? What's that you say? Did you say separate the variables? That is exactly right. So step number 1 is to separate the variables. All right, and we've got, now, not everything here is a variable. Like the k is not a variable, the l is not a variable, those are constants. It's only the t and the p that are variables. So when I'm talking about separation of variables, everything that I'm marking here in blue needs to go to the left-hand side. And everything else needs to go over there on the right-hand side, the t stuff on the right-hand side. Okay, so the 1 minus p over l is going to come with the p that's inside the parentheses. And so this is the way that we write it. I've got dp over p times 1 minus p over l is equal to k dt. All right, so far it doesn't seem very tricky. However, we do have a complex fraction, so we want to fix that. So the way that I'm going to fix that complex fraction is I'm going to get a common denominator inside the parentheses here. And that common denominator, of course, is L. So that's going to look like this, dp over p times L over L minus p over L. I'm going to keep going with that. Writing that as just one fraction, p times L minus p over L, right? And now the p that, or the L that's down here on the bottom, I can shoot it up to the top. Basically, I'm multiplying the top and the bottom by L, and then that's going to bring that, resolve that complex fraction, and we're going to rewrite it as L times dp over p times L minus p. Do you remember what I said in a previous video, that some books phrase the logistic growth model as jointly proportional to the population and the difference between the population and its carrying capacity? Yep, it happens right there. Okay, so that's still equal to kt, and we are finally ready to take the antiderivative of both sides. And you know what? The right-hand side is going to be a piece of cake. But the left-hand side, not so much. And the reason why is because we're going to have to use partial fraction decomposition. I'm going to do this thing in green. All right, partial fraction decomposition with just the left-hand side of the equation is going to look like this. Right? I have L over p times L minus p. Our variable here, remember, is p. It's like our x. This should be equal to some number over the first factor, p, plus some other number times the second factor, which is L minus p. Why is there parentheses there? It doesn't need to be. However, we do need to multiply by the common denominator, which is p times L minus p, in order to get rid of the fractions. And we have the basic equation, which will look like L is equal to A times L minus p plus B times p. And now remember, to solve the basic equation, you pick some numbers for your x, in this case p, to make that thing disappear. Some totally convenient values, and I'm going to say the first one is going to be p is equal to 0. If p is equal to 0, then that means b times p here is going to disappear, right? And I would be left with L is equal to A times L minus 0, which is just L. Okay, and then you divide both sides by L, and we get A is equal to 1. Boop. Now then, what else should we choose? What's our next convenient value for P? Well, we need the other factor to disappear, so let's choose that P is equal to its carrying capacity, L. In that case, L is equal to, this time that factor disappears, and we have B times L. Wow, that looks familiar. This means that B is also equal to 1. Boop. In other words, our partial fraction decomposition is this one. It is 1 over P plus 1 over L minus P. So that's what I'm going to replace this integrand over here with. So we've got antiderivative of 1 over P plus 1 over L minus P dP is equal to antiderivative of kt. All right, the first part, there's not going to be much issue. 1 over P, its derivative is just the natural log of the absolute value of P. Okay. The next one, though, there is going to be a slight issue here. Move this thing. No. Move this thing down here. Okay. And the reason why is because we have a composite function. I need to check it by u substitution and see what we have to fix. So our u should be L minus P. Remember, P is the variable here. So du is equal to negative dP. And I don't have a negative in there, so we're going to have to throw a negative inside of it. That negative is going to carry through our antiderivative, which will make this negative, the natural log of the absolute value of L minus P. Boop. Is equal to, I don't know why I said kt up here. Did anybody correct me? You probably should have, because it's dt, not t, dt. I had it correct up here. Anyway, so then the right-hand side will be kt, and don't forget your plus c, your constant of integration. All right, now we got to fix it. We got to solve this thing. We got to make it look pretty. And I'm going to use some properties of exponents over here on the left-hand side to condense these. Subtraction is going to turn into a quotient of logs. Natural log, absolute value of P over L minus P is equal to KT plus C. We need to get rid of the natural log, and we do that by exponentiating e to the. So we have the absolute value of P over L minus P is equal to, and you know what we've done before. We break that up as e to the kt times e to the c, and I'm just going to bring that e to the c up front. E to the c, remember, can be any positive number, e to the kt. It cannot be 0, and it can't be negative. All right. And then what I like to do is I like to get rid of the absolute value symbols. And when I do, I could have a positive solution or a negative solution. So I have P over L minus P is equal to plus or minus e to the c times e to the kt. And then the technique is, I'm going to replace that with something. Let's say I'm going to replace that with c. Make that thing c. It makes it a lot prettier, that's for sure. So our solution so far is P over L minus P is equal to some number C, e to the kt. And as it sits right now, it could be any positive number, any negative number, but it can't be 0. Because you can't raise C to some sort of number in order to get 0 from it. So that's the one that you test. Can C be equal to 0? Well, if C is equal to 0, then that means that P over L minus P is equal to 0. Cross multiply, that means that P is equal to 0. If P is equal to 0, then its derivative is also equal to 0. So now let's scroll back up here to the actual differential equation and see if that makes sense. If I plug 0 in for the dp dt is equal to k times 0, parentheses 1 minus 0 over L, I get 0 is equal to 0, which totally checks out. So the answer to that question is yes, C can be equal to 0. That's nice. All right, so far so good. All right, so the next thing that I'm going to do is totally unconventional. Let me try this again. The next thing that I'm going to do is completely unconventional. And it goes like this. I can't simplify the left side of this equation, but I could simplify it if it was upside down. I can divide the top and the bottom by p. And that's exactly what we're going to do next. We're going to take the reciprocal of both sides. So when I take the reciprocal of both sides, I have p. Nope, I don't. I have L minus p over p is equal to 1 over c e to the kt. But I'm going to continue to rewrite the right-hand side of this. This is 1 over c times, are you ready for it? E to the negative kt power, right? Because I basically took it from the bottom here and then brought it up to the top with a negative exponent. And the next thing that we're going to do is we're going to say, let's let 1 over c be equal to some other number. It could be c if we want it to be, but ordinarily it's written as a lowercase b. So we're going to take that 1 over c out and replace it with a b. Okay, so then our differential equation, or actually our solution, turns out to be our L over p is equal to, L minus p over p is equal to b e to the negative kt. All right, on the left-hand side, I can simplify this as L over p minus p over p, which is 1, is equal to b e to the negative kt. Add the 1 over to the right-hand side. L over p is equal to 1 plus b e to the negative kt. Remind me again, what are we doing? What are we solving for? I think that we're solving for p. And notice that the p is in the wrong place. It's in the bottom. But you know what? I can fix that. I can fix that by taking the reciprocal again. So we're going to take the reciprocal and flip this upside down, and we're going to have p over L is equal to 1 over 1 plus b e to the negative kt. And then the last step is to multiply the L over to the right-hand side of the equation. P is equal to L over 1 plus b e to the negative kt. And there you have it. There is the solution to the logistic growth model. The L that's up top, that's the carrying capacity. That's the carrying capacity. And it should be obvious what that number is from the differential equation. Now the b that's down in the bottom, it's not going to be obvious. We'll have to do some algebra in order to figure out what that is. And the k is also something that's obvious from our differential equation. Right up front, it's that constant or proportionality. Now I'm going to flip back to our cookie infection equation so you can see this equation happening right here. So up top we have something that looks sort of like the carrying capacity, which was supposed to be about 18, and then you have 1 plus, you have some b number that's multiplied times e to the negative k times t as the power. All right, so the next question is for p of t equaling L over 1 plus b e to the negative kt, find p of 0. In other words, we want to find when times equals 0, the initial population, what happens? We did something similar with the exponential growth model. We're going to do it with this logistic model and again see what happens. That would be this one right here. So I'm going to plug 0 in for t, and I'm going to write it like this. P sub 0, as in initial population, is equal to L, carrying capacity, over 1 plus b e to the negative k times 0. Well, negative k times 0 is 0, e to the 0 is 1, and so we have a simplified equation. Initial population is equal to L over 1 plus b, which is fine and all, but usually what we do is we take this equation and we solve for b. If we solve this for b, we can cross multiply it, and we would have 1 plus b is equal to L over initial population. And then I'd have to subtract over the 1. B is equal to L over P sub naught minus 1. All right, but then another thing that we do, another little trick, is that we get a common denominator between those two things, which would be P sub 0, the initial population. So this is L over P sub 0 minus P sub 0 over P sub 0 to get a B value of population, I should say carrying capacity, minus initial population over the initial population. Right, it's not quite as straightforward as the one for exponential growth, but all right, it's just simply carrying capacity minus the population over the initial population. All right, so I'm going to summarize all of these things on this next slide. Oh, you would crash. Hey, no worries. I'm going to go straight back to where we were. And it was approximately right here. So make sure that if you haven't taken any notes up to this point that you should, this is the logistic growth model summary. So if y is a differentiable function of t such that y is greater than 0, so we're saying our population is positive, that makes sense, and y prime is equal to ky times 1 minus y over L, L is the carrying capacity for some constant k, the constant of proportionality, then it solves like this. Y is equal to L, the carrying capacity, over 1 plus b e to the negative kt. The L is the carrying capacity that we initially started with. The k is the constant of proportionality. And as we just solved, b is equal to L minus the initial population over the initial population. All right, and then one super important thing to realize about this differential equation is as t, the time, approaches infinity, what's going to happen to the size of this population? Well, it's going to get closer and closer and closer to the carrying capacity L. And the reason why is this. As t goes to infinity, we have e to the negative infinity. E to the negative infinity is getting closer and closer to 0. 1 plus 0, this denominator becomes 1, and we reach the carrying capacity. All right? And then here we have our sample graph of one of these sigmoid, S shape. Up until its point of inflection, we have increased growth rate. After that point of inflection, we have decreased growth rate. That point of inflection, remember, happens at exactly half of the carrying capacity. All right, so that's going to do it for this particular video. In the next one, we'll apply this logistic growth model to a couple of problems.